Welcome again to the Applied Business Statistics course. In this session, we are going to discuss the seventh topic on time series analysis. The definition of time series is a series of observations related to time, especially when we have a fixed period of time like a year or a quarter of a year or half of a year or a day or fixed time. Fixed time, it can be a day, a week, a month, whatever. Fixed time and observations over a series of time of fixed intervals, same intervals. Can't be observation in this week and then after 2 weeks and then after 3 weeks and so on. It should be consecutive weeks or consecutive days or consecutive years or consecutive quarters or so on. So we're supposed to have a time series, a series of observations over time like exports, imports, production, sales, whatever. We have these over time, this observation over time, and we call them time series. So these time series usually contains some systematic trend, some systematic value. So we need to benefit from this systematic pattern and use this systematic pattern in forecasting future observations. So every time series, we believe that it contains some systemic patterns and some random effects also, random errors or random fluctuations. So there is every time series contains some components. Some of them are systematic components and others are just random fluctuations. And so like error in measurements or whatever. So in this topic, we are going to analyze this time series, this series of historical or previous observations in order to forecast the future observations. So the aim now is to separate from each other these fluctuations or this pattern in order to describe the historical pattern in the data first and also to present forecast by projecting the revealed historical pattern into the future. So we forecast future observations. So we have two goals. First, to describe the historical pattern and then to use this analysis in forecasting the future observation. So in the analysis of time series, we have two types of methods for identifying these patterns. I mean, systematic patterns. That's what I mean. These methods are either smoothing or decomposition. So either we smooth the time series like a curve, or the other method is the decomposition of the time series into its fixed patterns, right? So the random smoothing, the random fluctuations are removed. We remove the random fluctuation and keep only the systematic part, the systematic pattern. So the random fluctuations are removed from the data by smoothing the time series. So we have some fluctuation, we will remove this the random fluctuation and keep a smooth curve. And we want to use this smooth curve in we extend this smooth curve in order to uh, to forecast the future observation. But in the decomposition method, the time series is broken into its components, and the patterns is the combination of the systematic parts. So we have components, some systematic components here. We want to break the series into its main components and keep the random fluctuation. But the systematic components, we want to get them out from this time series. So the pattern itself is likely to contain some or all of the components, which the components are usually trend first, seasonal, and cyclical variations. So we have three components, and the fourth is the random fluctuation. Three main systematic components: trend, second is the seasonal fluctuation, and the cyclical fluctuations, or the cyclical component. And the fourth is the random, the errors, usually. So every time series either contain one or two or maybe the three components. So we want to select these components. So the pattern itself is likely to contain some or all of the following components, which we mentioned. First, the trend. The trend is usually long-term long-term change over all the series, So some systematic change, either upward or downward. That's what is called the trend. The trend is the overall change, maybe forward, backward, or downward over all the series, from the first point to the first observation to the last observation. There is some like this series. This one is there is a trend here, upward. This like straight line here. This is upward. So this trend is from the first point here to this last point. So this series, this time series has a trend. So the long-term general change in the level of the data with a duration of longer than a year, which usually over all the series. That is what we call a trend. It can be straight line or can be a curve, but usually most probably will be a straight line, and it can be represented in a straight line curve, first degree equation, like that, like a regression equation, where yt equals a plus bt. It is exactly the same as regression equation, but x here, instead of x, we have t. T is the time usually. So it is like a linear regression line. Linear regression line where x is the time, here t. Instead of x, we put t, time values. None or non-linear like curves, we may use smoothing method, but we will concentrate on the linear trend, and use the method which we know the linear regression method. It can be also exponential. This equation, like this equation, that's exponential. That's a curve also. All the other methods are curves. Can be exponential or logarithmic or whatever. So that's another equation, like nonlinear equation also, because it contains square here. This is nonlinear multinomial or and order multinomial. So these are curves, but we will concentrate on the straight lines, like linear regression methods, right? So that's the trend line. It's not exactly a line, it can be a curve or maybe approximated like a straight line here, but it's not exactly a straight line. This can be straight line, but it is most probably a curve. Most probably it is a curve. So, but we will concentrate, as we mentioned earlier, on the linear regression or a straight line trend, upward or downward. It can be upward or it can be downward. So, the seasonal variation is regular variation, like waves fluctuations. Fluctuations like waves can over time, so and it repeats itself every year or every few years. Every year or a few years can repeat itself, like spring, summer, autumn, winter. Spring, summer, autumn, winter. In spring, so the observations are large, high, and in summer it is less, lowest, and so on. And every summer is the same, the observations are high. Every winter, the observations are low, and so on, like that. These are called seasonal variation. Every season, so the season is not should not usually be season only the season or quarter of a year. Can be days also. The sales over days can contain seasonal variation also. Like every Thursday, the sales are high, and every Sunday, the sales are low. That's we call the seasonal variation, right? And the curve of this, the time series will look like that, like a small. Short-term variation, yeah, regular variation. These are what we call the seasonal variation. And we can, by the red line here, we can approximate it by a curve here. This time series can be approximated by a curve and to repeat itself every 1 unit, like a year or a week or whatever. So seasonal variation are usually associated with 4 seasons of the year, but maybe, as I said, if it is daily sales or whatever over days, it can be weekly, not yearly, and daily fluctuation, right? Can be like that also. It can be like that. Another example, or it can be like that. These are seasonal variation. These are examples of seasonal variation. So cyclical variation, this is third component, is the cyclical variations. That's cyclical component also. Wave-like movements, but it is medium range, not over all the series and not small range. It repeats itself, for example, 3 or 4 times over all the time series, but the seasonal variation or this seasonal component, it is short-term regular component, regular variation, short-term. But that's medium-term. The trend is a long-term. Over all the series, one trend the trend does not repeat itself. So just one straight line or one curve over all the series. But this cycle variation to repeat itself every long time. Like for example, daily sales on some types of goods, there is a seasonal variation over days and cyclical variation over seasons. in spring the sales are higher than summer, or the winter, and the less in winter, and so on. So there is cyclical over the seasons, for example. So the seasons are like medium term here. So this is the medium term variation is called cyclical variations or cyclical component. That's medium term. The seasonal variations are short term. The trend are very long term over all the series. That's the cyclical variation. And the series repeat itself every medium term period. We can also estimate this curve of the cyclical variation. The time gap between the beginning trough and ending trough is the length of the cycle. The length of the cycle, that's the length of the cycle. From this to this is the length of the cycle. And the same here, that's the length of the cycle, and so on. Right? So that's another example of the cyclical variation. And this is another example. As we mentioned, this anytime series can contain only one or two or maybe all the three components which that we mentioned here. The time period between the beginning of and the peak is called the expansion phase, while the period between the peak and the ending of is term contraction phase. Cyclical variation are often attributed to business cycle. In other words, to the ups and downs in the general level of business activity. Right? Seasonal and cyclical variations might appear to be very similar, seasonal and cyclical components. But as I mentioned, the seasonal variations or seasonal component is short-term one, while cyclical component is medium term, and the trend is the long term. So the cyclical variation is longer term than the seasonal variation. The last part is the random variation. Last part, every time series must have random variation. All time series contains random variation. Maybe some time series contains only random variations, but that time series is useless. It's useless if it contains only random variation. So any time series should contain some systematic thing, systematic useful component, so that you can use it in forecasting. So to benefit from it. But some series does not contain anything. But most time series in real life contain random variation and at least one of the components that we mentioned. So when this irregular component is strong compared to the regular components, it tends to hide the seasonal and cyclical variation. Sometimes the random variation is very big and make it difficult to extend the systematic components like cyclical and seasonal variation. It hides these components because it is, the random variation is big, so it hides the systematic variations. So that makes the analysis of this time series more difficult. Right? However, if we manage to capture the trend, the seasonal cyclical variation, and the remaining changes do not have any discernible pattern, so they are totally unpredictable. Unpredictable. So we have, as we mentioned, four components, including the random variation. We have four components. And as we mentioned, any time series contain at least one of these components. At least one of can contain all of them and can contain only one or two of them. How the components relate to each other in order to make the time series itself. So there are two models. There are two models. The first model we call additive model. So it is, in which model this model we assume that the time series is composed of addition of the four components. So the four components, or whatever, can be three or two, added to each other to make the time series itself. So the time series model used to describe the observed data by adding up the four components. Multiplicative model, the multiplicative model in which we assume that the time series is composed of the four components, or three or one, whatever, multiplied by each other. So we have two models, additive and multiplicative models. These combined with each other to form the time series. So we combine them by adding them up or multiply them by each other. If the trend is linear, those models look follows. So that's linear instead of trend of T. T is linear, and that's the seasonal component. And C, T, that's the cyclical component, and that's the random variation R from random variation. Or that's an additive model or multiplicative model. This is YT is equals, that's T. That's the straight line equation. Straight line equation multiplied by seasonal component multiplied by cyclical component multiplied by random variation. And this is the additive model, and the seasonal and random and cyclical all together are absolute deviation from the trend. And here, so they do not depend on the level of the trend. It's not because they are independent of the trend. They do not depend on the trend. Multiplicative model, the seasonal, cyclical, and random variation are relative percentages deviation from the trend. So it's the percentage of the trend. The higher the trend, the more the intensive these variations are. The higher the trend, the more intensive these variations are. So this time series which contain the increasing linear trend component. The fluctuations around this trend have the same intensity, and the fluctuations around this trend are more and more intensive, very intensive fluctuations here. So this is more popular. Both models have their own merits, and depending on the nature of the time series to be analyzed, they are equally acceptable. These are acceptable examples of time series. Now, this is a typical time series which we are going to analyze. So we will analyze time series like that, some observations, like 20 observations, and we have, for example, sales over days or weeks or whatever, and we want to estimate first the trend. We want to estimate the trend like that. It is a trend line here, upward, slightly going upward, increasing trend. And so we know that this is the first week, and then second week, and third week, and so on. And we have a trend, and we have also the seasonal variation. And we want to estimate each component, the trend and seasonal component also. Want to estimate both. That's a typical example in real life where we want to estimate these components and use these components in order to make forecasting, forecast future values of these weekly sales or whatever. So weekly data for future days or for future week. Now, the one approach of estimating the trend and seasonal variation also, but the trend there is one approach of the smoothing in general is called moving averages. Moving average can be 3 or 4 or whatever length. So we can start by calculating a 3-day moving averages. Day moving average, that's a simple approach of smoothing, and with the smoothing we can estimate the trend like straight line. So that's a way of smoothing, as I mentioned. For example, if we have this data and we want to estimate a 3-day moving average, so 3-day we calculate the means average for every 3 point, consecutive 3 point, we calculate its mean. Let's calculate the sum, then divide the sum by the number, which is 3 here. The sum of the 3 values, first 3 values. If you calculate the sum, you will find them equal 110, right? First 3. Then second 3, which are 45 plus 22 plus 25, they are 29. The sum is 29. The third group is 22 plus 25 plus 31 equals 78. So on. The fourth is 35 plus 31 plus 51 is 107. We put the result, the sum itself, in the middle of them, like with this sum of 3, the middle one. So, and this is the sum of the middle 3, and this is the sum of the middle, I mean the 3. The 3, and we put the sum is in the middle, and so on. So it is moving averages, not moving sums. It is moving average. So we want to calculate the averages. Average of 3 points. In order to calculate the average of 3 points, we should divide by 3 because 3 points moving average. So divide 110 by 3, you will get this result. And this by 3, divide all of them by 3, you will get. That's the 3.3 moving average, 3-point moving average. We can calculate also the 5-point moving average. As we described that, this is the sum 110 over 3. Right, so no moving average values here. We can calculate also 5-day moving average is the same, but instead of having 3 point and calculate the average of 3 point, we calculate the average of 4 point moving average. So if we calculate it in the same way and we plot the original time series, this is the blue lines, that's the original time series. Then the red line is the 3 point moving average. Then the green line is the 5 point moving average. Calculate them. So you will find the 3 point moving average represent the trend or the series more uh, more يعني better than the 5 point moving average, more exact. So this figure suggests that the longer the moving average period, the stronger the smoothing effects. No, the longer the moving average period, the stronger the smoothing effects. That's more smooth. If we have 4-5 point, we go like that is approximate to straight line. But this, the 3 point moving average contains more fluctuation than the 5 point moving average. If you perhaps if we make 7 point moving average, it will be exactly a straight line. So they are roughly more better than this line. So if you increase the order of the moving averages, then you will get it more approximate to the straight line. So this also the shorter the smooth series also. When the moving average period is relatively large along the random variation, the seasonal and cyclical variations are also removed, and only the long-term trend can be revealed. So if we make the moving average long or large, then we only have a trend only. The seasonal or cyclical variation will be removed. So, what if an even number of periods? We have seen that we have 3 point moving average, that's odd, and 5 point moving average, that's also odd. But what about the case? What is the case if we have even number like 4 or 6 or 8 or whatever? What do we do? What's the difference? What that is made if we have even number? The difference is we cannot put the figure in the middle. We cannot put the figure in the middle. So for this, in order to put the figure, the results in the middle, we have to make another moving average for the series and make centralized moving average in this case, centralized moving average. For example, if we calculate 4 period moving average, 4 must be placed in the middle of the window, in the middle, on the line, not between two values, between the second and the third observation involved in the arithmetic mean, not opposite to one of the observations, between two observations. This makes interpretation of the graphing more difficult. We prefer to use centered moving average in order to get it back to the middle of the data, which in this case are the 2 period moving average, 2 point moving average of the 4 period moving average. So we make 4 point moving average, then we can make after that 2 point moving average and then center the data again, or center the results, the averages themselves again in the data. Example, Example 1, calculate the 4-day centered moving average. That's the data, and this is you see the moving average, 4-point moving average. It is not exactly opposite to the values itself. So that's a 4-point. 43 plus 45 plus 22 plus 25 over 4. It will be 33.8. That's the average of the 4 points. But where should we put this result? 33.8. Where should we put it? Up to the second value, 45, or third value? So it's not in the middle. We can't put it in the middle. So we should put it really in the middle between these two values. Between these two values. And 30.8, and between these, this is the average of the 45 up to 31, and we should put it between these two values, between them, and so on, etc. In order to be center them again, we should make again for these values the 2-point moving average here, and put again in the middle. We will start then on the here in the center. It will be again center opposite to 22, but we lose 2 points up and 2 points down. All right, and that's what happened. So that's 2-point moving average. So this is the average, centered one. Right? This is centered 2-point moving average in order to center the moving average. The second type of smoothing, we mentioned moving averages, the way method of smoothing, and there is another method, second method of smoothing called exponential smoothing. In this method, we use the following formula: St equals W times Yt plus 1 minus W times St minus 1, where St exponential smoothing value for time series t, and St minus 1 again exponential smoothing value for the time period not rt minus 1. So t minus 1, and Yt is the observed value for the time series and time period t. And W is smoothing constant. Any constants could be 0 to 1. The method of choosing W is arbitrary and difficult sometimes. That is not accurate. For this reason, we will not concentrate on this method as smoothing. It is rarely used, this method. The moving averages method are more useful than this. Not many people use this method, so we'll not concentrate on that, but if you are interested, you will find the rest. You can read it here. So that's what we want to say. So we will not describe the rest of these slides here that describe the exponential smoothing, because we will only concentrate on the moving average method. See you next session on more examples and more discussion on time series analysis. See you. Bye bye.